We'll continue with the discussion of advanced strength of materials. In today's lecture, I'll be covering an example, few more examples on the idea of strains. And so far, what we discussed is the idea of stress, the concept of stress, and stress is a force-like quantity that reacts to the external loads applied to the system. So that's one idea that we covered in this class. And we've covered now the idea of strain in the previous lectures. In this lecture, I'm going to give a little more examples on how to look at this concept even further. Recall that the idea of strain is to have a measure of localized deformations in a system. So let's look at this example here, which is a classical example that can better make you understand what is going on with strains, like what is the concept of strains. So what we like to do in this particular example, we would like to determine the strains in the body of material, the one that you're showing below, and I want to find the strains at a particular point in the body. And I want to find the strains in this particular point of the body, which goes, it undergoes into the deformation that's shown below. So it starts with the solid lines A, B, Q, C, and Q moves to the location Q prime, C moves to location C prime, and A moves to location A prime. And so it's useful to understand how things are moving around so that you can do an analysis of what's happening here. So the question that's asked is, what is the principal strains and what inclination the principal strains occurs at? So the first questions are, what is the strains of the body of the material? And the second question is, what are the principal strains? So if you recall, the axial strains given by this equation, but that's approximately equal to the change in the deflection in the x-axis divided by the original length. And recall that in this case, deflection U is to the right and deflection V is upwards. And this strain here, epsilon xx, is measuring the relative change in deflection in this direction. That is what is going on there. But recall that we're calculating the strains about Q in this example. So what do I need to do? I need to figure out how to calculate delta U. I know the original length, delta X. So let's look at that. I have delta U, which is this, the deflection of this point to the right. So basically the deflection in the horizontal direction, that point C moved to C prime, an amount that's 0.175. So that's this number here. This point Q moved to Q prime, an amount that's 0.0075. So this is that amount there. And then the original length of CQ is known as 150. I know what the length is. From here, Q to C. And that amount is 150. So you can see that there. So that's how I can calculate the strain in the axial direction, which is this direction, by looking at how point C moved to C prime and how point Q moved to Q prime. I did not look at the deflections at point A because the question is, what is the strains in the body of material at point Q? So I'm looking at this location, not above, but I could also do it above if I wanted to. When I do the calculation, I get 667 microns. So yeah, the deflection U is measured positive in the right hand side. So if is pointed right, because the x-axis is pointed to the right. That's why. And there are other ways we could have done this calculation, but this is one of them. But you could create like a coordinate system 0, 0 here, figure out what the coordinates of this point are, figure out where the coordinates of this point are, figure out the new coordinates of where this point are, and use that to figure out basically what does it change in length. Because as you recall, epsilon xx can also be equal to the final length minus initial length divided by initial length. And what I could have done, I could also look at the coordinates of this point. So the coordinates of this point is point Q prime. It moved to the right, 0.075. If point Q is a 0, 0, so let's assume point Q is a 0, 0. And then it also moved downwards an amount of minus 0.05. So that's where Q prime is. That's this one here. And point C prime, which is this one here, is located at a location of, so if this 0.175, it moved 0.175 is 150.175. And it moved downwards actually also at minus 1.25. So you guys can find the length, the final length by subtracting these two numbers. That's another way to do that calculation. So that's 150.175 minus 0.075 minus the initial length, which is 150, because it started, the distance between Q and C started at 150 divided by 150, and you'll find that you'll get the same answer as this if you do it this way. So two ways to do it. Both ways works just really well. So continuing on, now I'm gonna calculate epsilon yy. Epsilon yy is the strain in this direction, right? So that's what I'm looking for there. I'll do the same calculation. So partial V, which is the deflection upwards, and the change in length in the y direction. Okay, so delta y is what I have there. So let's start. So in the vertical direction, what I have is point A over here and point Q over here. So that length is 100, which is what you see here. The coordinate YA minus YQ is 100. And then the relative deflection of point A, it moved upwards an amount 0.025. So that's why I have that there. It moved to this location here. And then the point Q moved downwards an amount that's 0.05. So it's negative there because it moved downwards. I calculated as 750 and you're done. I can also use the method I had used earlier, this method, but I think you follow so far. I can do it very quickly to illustrate. So point Q moved to Q prime. I had already calculated that there. So Q prime, I'll just copy and paste from before. So I have to copy it again. And then point A moved to a new location. It didn't move anything in the x-axis. It moved upward 0.025. So the new coordinates are 100.025. So strain YY is the final length minus initial length divided by initial length. The final length can be calculated by subtracting these two numbers in the y direction. So I get 100 plus 0.05 minus 100. And that's going to give me the same answer as what I got here. You can see that. That 100 is this 100. This 0.25 plus 0.05 is basically this, because this 100 cancels with this 100, and you get the addition of these two numbers, which is exactly the addition of these two numbers. Let's look at shear strengths here. So shear strengths is the partial v respect to x plus the partial u respect to y. And physically, what it means is it started at 90 degrees, but it changed angles to this amount. So gamma xy represents the angle change. That's what it represents. So partial v respect to x plus partial u respect to y is approximately equal to the change in v, the relative deflection, divided by delta x plus the relative change in u divided by the change in y. And so here I want to be careful. So I want to look at CQ. I want to see what the change in angle is, which I can calculate fairly quickly. So that's going to be VC prime, the vertical deflection of C to this point here, you can see, but the downward deflection, minus VQ prime, because this point moved downwards also to this point. Okay. Divided by XC minus XQ. So XC, the coordinates of this point, minus XQ. I know this is 150 at the bottom. And then the relative deflection in the axial direction. Remember, U goes right and V goes up. Vertical deflection versus horizontal deflection. I do the same thing. The point U at a point A move to this point. Point Q move to this point horizontally. So I'll go ahead and by the way, this minus that is 100. I plugged it in, so let's examine each of these. So VC prime, that one moved downwards at amount 0.0125. You can see that there. Move from here to here downwards. That's this amount. And then VQ prime, this point moved downwards also, vertically, 0.05, and that's why that's negative. And then this distance, I already know what it is. That's the distance here. 150. I gave it to you here. And now I look, let me clean this up so it's not too much information. Let's examine now UA prime. UA prime moved an amount 0.0, this point A did not move to the right at all. It stayed there in the horizontal direction. So that's 0. Point Q, move to the right and amount 0.075. So that's that. And YA minus YQ is this distance here. That's 100. And when I do the calculation, I get that the shear strain is the number shown here. And that represents the angle change that you have due to this deformation. So, continuing on, principal strains. I have the formula for principal strains. Epsilon XX was found earlier. If you recall, we got over here 667. I guess I rounded it to 660. Epsilon Y was found at 750. You can see that here. I should have rounded that, but that's fine for now. And then I have minus 1250, which is this number here for shear strain. I do the calculation, and because I have the plus minus, I get two numbers, 1335 microns and 82 microns. Remember, this unitless, there's no dimensions here. What inclination happens? I'll plug in gamma XY and epsilon X and epsilon Y, and I do this calculation here, and one of the angles will be 43.1. But you'll also get another angle when you do it. And it'll be 90 degrees apart. And so to figure out which of these number corresponds to the 43.1, you can go back to your strain transformation equation, plug in epsilon XX or epsilon YY, gamma XY, and that's theta that you calculated previously. And when you do the calculation, you get 82. So you know that this 43.1 goes with 82, and at 90 degrees apart, the other strain, 1335, is the one that corresponds to that one. So what you're really looking at here, to make it more clear, these X and these Y, and normally have the strains in this way. And so I was trying to find the principal planes, which occurs at an angle of 43.1, meaning if I look at that same box, this is going to be 82 microns, and this will be the 1335 microns. Okay, there's another way to do this. I have the strain tensor here that I can write down. Obviously, the strain tensor is 3 by 3, but the other shear strains are 0. You can keep them there if you want, but for 2D problem, it doesn't matter. It won't do anything. So that's the strains I got earlier. I just pasted them here. Notice that it's divided by 2 here. So be careful with that. And so now I can subtract lambda from the diagonal. And if you look here, I subtracted epsilon p. You can subtract whatever you want, whatever variable you want. And then I multiply. In case you forget how to do this, I'll do it quick. You multiply these two. And you subtract these two, multiply. And when you do, you can remove this micron thing. Don't keep you don't get confused. You get a quadratic equation on this epsilon p. So this epsilon p is in a quadratic equation. And then you can use a calculator to figure out what the epsilons are. And you can see that the answer I got here is the same as the ones you get with this equation. We can also find the corresponding eigenvectors. All you have to do for that, you can substitute one of these into this. And I did it here at the bottom. And I don't know what the normal vector is yet. But what I can do, I can write my two equations here, as you can see. I'll choose one of them because they're not independent of each other. I'll select the first one, but if you select the second one, you get the same answer. I solve for L1 as a function of M1, but I know there's a unit vector, so I plug this into the fact that L1 squared plus M1 squared is 1. I know L1 as a function of 0.94. I plug it in there, and I solve for M1. So, because I know M1, I can plug it back in here to get L1, and the eigenvector I get is this one. You can repeat with a second eigenvalue to then determine that second eigenvector. Now, I'll plot it for you real quick. You can see that if this is 1 and this is 1, it moved to the left over here somewhere. I'm kind of doing it visually, and it moves. So basically somewhere here. So that's how that eigenvector is oriented, which is not different from what I got here when I did it visually. I mean, this is not a very good drawing, but you can see that the vector is pointed in the same direction as I had shown earlier. I pointed that way. Obviously, I'm not using a compass or anything like that, so I'm kind of visually looking at it. But that is oriented. And then the other vector is going to be oriented this way. So this one corresponds to the larger number, and this corresponds to the 82. But two ways to do the problem, and we need to be familiar with both methods. I want to point out something quick. So the diagonal terms, which are this, when they're transformed to the principal strains, you get no shear strains in that principal plane. I want you to notice how when you sum this and you sum this, they'll be equal, because these are called invariants. So 667 plus 750 will give me the same thing as when I add these two numbers. 1335 plus 82. So that's something to keep in mind. Like, if you know these two numbers and you calculate one of the eigenvalues, just subtract to get the 82, right? Because the summation of the diagonals has to be equal because of the invariant properties that these materials have. That's and the other thing I would show you later is that when you sum the diagonals, these strengths actually correspond to the change in volume. Very useful quantity and very useful thing to know. Very, very useful for applications in real life.